Okay, everyone, good morning. We're going to get started. My name is Pamela Robinson. I'm a professor at the School of Urban and Regional Planning here at Toronto Metropolitan University, and I'm pleased to be moderating our session today, which is hosted by City Building TMU, where I'm the academic director interim. To begin, I'd like to start with acknowledging that we are in the Dish with One Spoon territory. The Dish with One Spoon is a treaty between the Anishinaabe, the Mississaugas, and the Haudenosaunee that bound them to share the territory and protect the land. Subsequent Indigenous nations and peoples, Europeans, and all newcomers have been invited into this treaty in a spirit of peace, friendship, and respect. We're happy that you could join us today for this session with some of our leading researchers making up the Center for Urban Energy, or CUE, here at Toronto Metropolitan University. CUE is an academic industry partnership focused on delivering novel, tangible, sustainable, and affordable solutions to pressing energy problems of today and leading into tomorrow, which you'll soon see. The leadership of this center comes from Dr. Bala Venkatesh, who's a professor in electrical and computer engineering at TMU and a top expert in electric power transmission and distribution systems. Under his leadership, CUE has worked with over 25 industry partners, including utilities that you might know, such as Hydro One and Toronto Hydro, focusing on applied research to move forward and to understand the impacts of the energy sector on consumers with accessibility and affordability as top of mind. Today, we're going to focus on some of the tangible and applied research projects happening at CUE under the direction of Dr. Thiago Fernandes and Dr. Ahmed Khwaja. So before we dive in, I just want to offer a few housekeeping notes. Today's presentation is about 25 minutes of moderated discussion, followed with a chance for people who are participating from the audience to offer questions that I'll have our panelists ask. If you look at the bottom of your Zoom screen, you'll see a Q&A function where you can type in your questions. You can also look at the questions that other people have posted. And if you like them, you can vote them up just to make sure that we get to the most pressing questions first. As you know, when you entered the room, this session is being recorded. You'll be able to find the recording on the City Building TMU website in the following days. Make sure you're subscribed to our newsletter so that you can keep up to date with all of our latest information. Okay, enough with housekeeping. Let's get on with the show. I'm really excited to introduce our two guests today. First, I'd like to introduce Dr. Thiago Fernandes. He's a research fellow at the Center for Urban Energy with a PhD in electrical engineering. His research interests involve transmission and distribution systems analysis, energy efficiency in buildings, and grid-connected battery storage systems. Our second guest today is Dr. Ahmed Khwaja, who's a research center at the Center for Urban Energy as well. And his PhD focuses on signal processing and telecommunications. He's looking at how machine learning and optimization of problems inside smart grids can be solved. And he's specifically looking at electricity load forecasting, smart meter data obfuscation, and load disaggregation. So today, as you can see, we're going to cover a range of interesting topics related to the present and future of energy related work in our system. So without further ado, let's get going. I think what I'd like to do is just start with a general discussion about the Center for Urban Energy, where both of your research is housed. What are the major themes or problems that you're looking at in terms of current projects? And what kinds of gaps or understandings of technology are you and other colleagues at the Center for Urban Energy hoping to address? Most importantly, I think, given that this is City Building TMU, can you talk to us a little bit about how that research impacts our city and our urban regions? And what are some of the urban contexts for which consistent energy supply is the most important? Thiago, let's start with you. Thiago, you're on mute.
Sorry. I've been here for 4 years. I came as a PhD visiting student. Then I'm here now as a postdoc, right? I can tell you that some of our projects include energy efficiency, in which we study means of using less energy to perform the same task, methods to accommodate the increasing penetration of distributed energy resources into the distribution grid, right? Because there are many implications regarding the integration of distributed energy resources into the grid, okay, such as overvoltages, reverse power flows, and overload that may lead to brownouts or blackouts. And we study ways to mitigate these implications and safely accommodate increasing amount of these resources into the grid. And thirdly, we also study energy storage, right? So in which we apply, and it's basically batteries for reducing period congestion, mitigating the variable nature of renewable generation, such as photovoltaic and wind generation, and also as a backup for industries, a backup power, to provide services to utilities and to the IESO, which is the Independent Electricity System Operator in the province. And finally, to perform peak shaving and energy arbitrage in large commercial buildings to reduce energy bills in these buildings mainly, right? Now, as you ask, why is it important, right? The continuity, consistency in the supply of power. So I can give you two examples. These examples involve critical loads. So basically, a hospital, for example, is a critical load that may have a continuous energy supply, right, of power, and also with quality, basically to ensure patient well-being, and also because there are medications and products that should be kept at low temperatures. So this is one, right? And another critical load would be when we talk about industries, for example, in a pharmaceutical industry or aluminum industry, where we need to also have a continuous and supply of power, and also with quality. So when I talk about quality, I'm talking about, because the supply should be within some regulations, should be conforming to regulations. So this is quality. And some machines in industry are very sensitive to this quality. For example, the voltage range, also the frequency of the supply. So if something goes wrong, then we may lose, for example, an entire process in an aluminum industry, which again, we're talking about losses in millions of dollars. And also, which is worse, this could put people's lives at risk, right? Because there are machines that need energy to provide protection. That's how I see it.
Thank you. Ahmed, do you want to add to that?
Yeah. In addition to what Thiago has explained, some of our other projects involve working on research models, which can help ensure reliable electricity supply to consumers, as well as reduce their cost that is transferred to them in the form of electricity bills. At the same time, also ensuring that their privacy is also protected. In addition to that, we have also worked on modeling of new technologies, for example, addition of EVs, electric vehicles, and how they will affect the present energy infrastructure, as well as, for example, management strategies or other aspects. So in terms of an urban area, all of this is very important towards achieving a net zero emission goal, because it's well known that globally, almost everywhere, the urban areas consume almost more than 2/3 of the electricity supply. In terms of research, gaps and what is not there and what new we are trying to address. So our first goal is to actually make models that are not only accurate, but also consistent. So we are working towards consistently accurate models. The second is to have some privacy protection schemes, for example, which can be implemented in with current hardware without any need of extra hardware. And then also in terms of electric vehicles, we have worked on modeling such that it can allow, for example, an electric vehicle to be integrated in a smart home.
Okay, thank you. So it's clear that there's a range of research that's happening that has both system-wide and individual impacts. And I really appreciate how you've covered that full scale of the work that you're doing. It's pretty clear now that our cities and our decision makers have to start thinking about new ways to do adaptation and work to make sure that energy service provision is consistent and effective. So I think, one of the practical ways we can think about this is when we think about electric vehicles. right? In terms of how do we start to shift from fossil fuel based mobility to electricity based mobility. And one of the ways in which we do that comes with people driving individual EVs. So Ahmed, you've been working on modeling related to EV charging. If we have listeners who use EVs, we have a friend who has an EV and they're always monkeying around with their app, trying to find the charging station, trying to figure out if it's working. But there are bigger systematic things that the people need to focus on. So can you tell us a little bit about the research that you're doing and how the rollout of your research will lead to a more efficient and user-friendly charging system?
Yeah, so the basic motivation of research on EVs is to actually study their effect on the current energy infrastructure, as well as other aspects, and then to prepare for that effect and then mitigate any changes that may occur. So although it has been shown that at an aggregator, at a very large scale, the system is not really affected too much, even in the foreseeable future, by the inclusion of EVs. And then by effect, I mean, for example, like their daily peak load, how much would it increase? So at a system level, it won't increase that much for the foreseeable future. But at a small scale level, this effect is a bit more significant. For example, like in some research, it has been shown that in like a 150 home neighborhood with a 25% electric vehicle penetration rate, so the daily peak load would change by 40% actually. So this motivated us to actually look at individual EV charging behavior modeling, because another reason is because like most of the EV charging is carried out at home. Like what this does is actually it provides, it models the behavior of the user, and then it will predict like how much charging will be needed at a particular time or at a particular hour. And how it can help is that it can be integrated in like a home energy management system or with a smart charger charging mechanism, and then it can ensure that an EV is charged reliably, but at the same time it's charged at such a time where it will have less effect on the daily peak load. And then secondly, if, for example, there is like, let's say, a solar panel available in the home, so it will coordinate the charging in based on that, the prediction of the charging needed. It will coordinate the charging in such a way that the electric vehicle is basically charged with the solar energy. So in effect, actually really achieving like a net zero emission system, which is actually one of the major goals of having the EVs.
Okay, thank you. All right, so let's move from thinking about cars to thinking about buildings. We all know that right now energy costs are a concern at the individual household level, at the institutional level, and in private sector businesses as well. And one of the subsectors of folks in Toronto who are deeply thinking about energy costs, energy efficiency, are people who provide affordable housing, especially in vulnerable communities. And so Thiago, we know that you've done some work with Toronto Community Housing on a research project to help them figure out how they can reduce energy costs within their portfolio, which we know their massive real estate holdings in Toronto are significant. Can you tell us a little bit about this project and how you came to work with TCH and what you've discovered, and ultimately what the research finds and what you might recommend to anybody else who's in an agency with a large real estate portfolio?
Yeah, so the project with Toronto Community Housing is about the establishment of methods for increasing energy efficiency in large residential buildings, right? So TCHC wanted to reduce costs in its portfolio, energy costs in its portfolio in a cost-effective way. So they came to us and we proposed 3 technologies to them. So these technologies are energy storage, batteries, voltage regulation, power factor correction, and photovoltaic generation. So Toronto Community Housing portfolio includes many buildings, most of which are Class B customers, and there's only one Class A customer. Just to give you a quick definition for Class A and Class B, so it depends on or the average monthly peak demand of this building. So if it's from 50 kilowatts to up to 1 megawatt, then the customer is classified as Class B. If it's above 1 mega, the customer can be classified as a Class A customer. So these classes of customers are charged differently. So I don't want to dive into like many technical details, but Class A customers, for example, can eliminate global adjustment charges, which constitute like the greatest share in the energy bills of these buildings, whereas Class B cannot. So our main findings basically were that for Class A customers, the best technology is energy storage. With energy storage, it is possible for these customers to reduce up to 50% the energy bill. So we're talking about bills that can reach $1 million in a year. So a 50% reduction would be incredible. But for Class B customers, so neither energy storage nor photovoltaic generation are cost effective, basically due to the high cost associated with these technologies. So for Class B customers, the best technology is voltage regulation. With voltage regulation, our studies concluded that it is possible to reduce 5% in the energy bills, which is not very much significant as 50%, of course, but it's also good if you consider that these bills can reach up to $50,000 monthly, right? So we're talking about 5%, then $2,500 saving per month, so which is also something good. And there's also advantages regarding this technology over the other two. For example, voltage regulation is much cheaper, so you just need basically a transformer. Maintenance is also something that you should not worry about for this technology. Another thing is it lasts, for a long time, unlike the other two. So it's also a good option. So again, energy storage for photovoltaic generation are still very expensive. And as we're talking about large buildings, then so the battery and also the PV system would have to be large, and which, of course, are expensive, and they are not cost effective for building in the short term.
Okay, thank you. And Thiago, how reproducible is the work that you've done with Toronto Community Housing for other clients? Would the method be a lot different with other organizations, or how transferable are those findings?
Yeah, so because it just depends on the customer class. So it can be applied to any other building, Class A or Class B. So and by the way, we're trying to go to the market with this software that we created, and also with the results of this work, of course.
And so could, for example, like the Toronto District School Board be a potential future user of that software?
Yeah. So so pretty much any building that's charged as Class A or Class B. So I said residential buildings, but like from the point of view of the utility, for example, Toronto Hydro, then this is a large commercial building. So
shopping malls.
Yeah, shopping malls.
Yeah. So hey, Oxford Properties, if you're listening, or Cadillac Fairview, they should get in touch. Yeah, good way to save money on their energy bills. Okay.
Yeah.
Okay, awesome. Okay, so we've talked a little bit about storage, we've talked about billing and about provision. I want to focus a little bit on electricity consistency. I think, when you live in Toronto, for the most part, when you're lucky, you don't think about the consistency of the electricity supply. Unless, we have a weird, extreme weather event, or there's a glitch or something like that. But when our power goes out, A, we're surprised, and B, it doesn't happen that often so far. But we do know that with extreme weather events, particularly watching the storm season that hit the East Coast of North America, we saw significant disruptions to energy supply, electricity supply, and grid maintenance challenges. So lots of people here may have some direct or indirect experience, and we've got a really good opportunity with the two of you to weigh in on some of your research thoughts. So Ahmed, let's start with you. What's the importance and the value of doing electricity load forecasting to make sure that we've got a smooth electricity supply? And how can it actually help in terms of reducing the cost of electricity that's passed on to consumers? So you have both a preventative and a reactive piece. Tell us a bit more about that.
Yeah. So to answer this question, perhaps it's better if I share a very simple slide. Yeah, so this is basically actually a very simple overview of an electrical grid. So basically what is happening is that as consumers, whatever electricity we are consuming, it's being transmitted by our smart meters to a distributor. For example, a distributor at a Toronto level is Toronto Hydro. And then the distributor aggregates the data and then further transmits it to other entities like generation and transmission entity, for example, like Hydro One, and then management entity, which can be IESO for Ontario. So what happens is that the management entity, the one at the very top, it uses the data that's received, the aggregated data. It uses that data as well as a load forecasting model, which is based on the data and weather parameters and maybe time of the day and other parameters to anticipate how much electricity will be used at a certain time or a certain day, a certain month. And then based on that, it arranges for that much electricity to be available by buying it. So first of all, load forecasting helps in making sure that a particular amount of electricity it's available to supply to the consumers as and when needed. So that's the first role of electricity forecasting. Whereas the cost is concerned, so basically the cost of buying the electricity by the management entity, it's actually passed to the consumers. So if it's already known accurately how much electricity will be consumed, and that has been bought much in advance. So it can help in reducing actually the cost of buying the electricity. Eventually, actually, that will be reflected in a reduced electricity bill. So basically, this is the second aspect in which electricity load forecasting shows its value. And another so the important point here is to have accurate electricity load forecasting, so that for example, if there is under forecasting, so the management entity may not have a set sufficient resources on the side, and then either as a very a really worst case scenario, there would be a power breakdown, or there would be purchase of electricity at the last moment, resulting in a higher cost passed on to the consumers. Or in the other case, if there had been over forecasting, so basically what would happen that extra resources had been purchased but had not been used. So basically, if that had been forecasted more accurately, the consumers would not have to bear those extra expenses. There is a very famous statement always basically facts given in research papers that for example even a 1% increase in forecasting accuracy can result in $1 million or even more savings over 1 year. So this is how accurate electricity load forecasting can help in reducing the cost of supplying the electricity, and then eventually what the consumers have to pay. We have also worked on developing accurate load forecasting models by using machine learning and deep learning techniques. And then what we are trying to achieve is not only models that are accurate, but models that are consistently accurate.
Okay, thank you. All right, I'm going to get you to take your share screen off. Thiago, I want to swing around to the other end of the system. So Ahmed talked about systems-wide change. Let's focus a little bit about the role that grid-connected batteries can play. Can you tell us what battery storage offers in terms of continuity, in terms of electricity supply, in the case of extreme weather events, and how that works?
Okay, so a grid-connected battery, a large-scale battery, can be employed for different applications, which depend on the system operating state and also on where this battery is located. So these states are basically emergency states in which the battery can be used as a backup power. So as I said, in a case of an extreme weather event, so this battery will be used to supply power to its load. And the location for this, in this case, is behind the meter. So this battery basically will be inside a facility behind the meter of this facility. So there's also restorative state in which the battery can be used to provide the so-called ancillary services to the ISO, such as black start, operating reserve, and some others. In normal state, so in the normal state, the battery can provide demand response to alleviate feeder congestion, also reactive support and voltage control to improve the voltage profile along the system. And also in situations where a battery would be a cheaper solution than a system upgrade, this battery can be used as to postpone a feeder upgrade. So yeah, so that's how a battery, a large scale battery, can be used.
And Thiago, do you foresee over time, half of people in Toronto don't live in a single family home. People live in buildings where there are 2 or 5 or 100 neighbors. Do you foresee higher density buildings like apartment buildings or condominium buildings starting to invest in shared battery storage?
Yeah, shared battery storage will be a good solution because the prices regarding this technology are still very high. And so this battery could be used as a backup power. But as you say, in Toronto, the energy supply is pretty good. So, I mean, this battery will be used, I would say, just a couple of times in a year. But it could also be used as we use for Toronto community housing to perform peak shaving or energy arbitrage, which is basically charging this battery when the energy prices are low and using this energy when the energy prices are high. So to provide costs to the people in the building, right? To reduce energy costs.
I think it's one of the interesting connections between your pieces of research, which is like, if we can get better at forecasting and modeling demand and try to basically hack the price structure, then we can use the new storage technology to pay less for the energy we need with more consistent provision, whether it's provided on a day-to-day, everyday use basis, or we're ready and waiting in case we need it for emergency supply. And so I think that's interesting connection between your work. I've got a couple more questions for you. I just want to remind our attendees that you've got the chance to ask your own questions in the Q&A box at the bottom, which we're really looking forward to getting to in about 5 minutes. So let's focus, we've talked about big systems change. We've talked about big institutional users. Can we scale your research down to just kind of think about everyday folks living in communities? What are you ultimately trying to achieve in terms of the community impact of your work? Because this work is really applied, right? The goal is to make a difference on the ground with real people in real places. So, Thiago, let's start with you. What are some kind of everyday benefits or impacts that people may find from your research over time?
So I can give you 2 examples for this. So so as I said, we study in the center, we study methods to accommodate more distributed energy resources. And for example, in Ontario, the energy mix includes a lot of wind generation. So wind generation is greater at night when the demand for energy is low, right? So what happens many times is that this generation is curtailed, or the energy is sold very cheap to all the provinces, or even to the US, to New York. So if we could have batteries in appropriate locations to store this energy at night and then to inject it back into the grid, at periods of high demand, then again we could reduce energy costs to the entire province, and so that will be an application of energy storage. And secondly, we can also improve quality in the supply of power. If it's necessary, we can, for example, have more PV generation, because this, like renewable generation, usually have a variable nature. So you can also, with batteries, you can also compensate for this, and you know, eventually reduce the energy costs, which is the main idea of you know, using storage.
Okay, Ahmed, what about you? Thoughts about how to bring your research down to impacting everyday people?
Yeah, so actually, as I mentioned in response to your question about load forecasting, so basically it's something that is happening at a higher level and behind the scene, but it's actually trickling back to the consumers. So whatever is like any better load forecasting approach would eventually affect each and every consumer. So that's like one aspect. Another aspect is, of course, like related to the reliable supply of electricity to the consumer, because that's what each consumer wants. In addition, actually, the work on electric vehicle charging behavior prediction, that's actually focused very much on like either an individual consumer or like very small group of consumers. And that is something which can be adapted for use in like a home energy management system, or maybe also like for making sure that the cost of EV charging is reduced, for example, by shifting the charging by this home energy management system or smart charger, or also to make sure that if the user has some other like renewable energy sources present, so that can be used to charge the electric vehicle. So basically, both these topics, first one is indirectly affecting the consumer, whereas the second one has more direct implication on a consumer or a consumer.
Okay, thank you. Okay, this is my last kind of big question, and we'll go to the questions from the audience. You've talked a lot about consumers, and after all, end users or people have a lot to do with how our energy ecosystems function. Ahmed, you've talked in your research when we met before about data obfuscation, which sounds very mysterious and clandestine and exciting. What role does data masking play in terms of the ways in which the energy system can function smoothly? And how can data obfuscation help increase consumer confidence in smart meters?
Yeah. So basically, as shown in the slide earlier, each consumer is actually transmitting the electricity consumed, the amount of electricity consumed to the distributor via the smart meter, and that's like periodic. And then the distributor would aggregate the data from a group of consumers, and then not only send it to other entities for like carrying out electricity load forecasting, but also to also use it at its end, for example, for proposing time of use tariffs. It would basically analyze those data to propose time of use tariffs. So basically one thing is that we need those smart meters to achieve some, they have some benefits. Now what happens is that because we are periodically transmitting the data, it raises some privacy concerns at the end of the consumers. Why? Because actually with those data that are being transmitted, and the higher the frequency of transmission, actually you can tell, for example, what type of appliances a consumer is using, whether the consumer is at home or is absent. There are also some like concerns that, you know, some like their data might be sold to advertisers, for example. So on one end, actually, we need the smart meters, but on one end, like on the other end, actually, there are also some concerns. So this is where like data obfuscation or data masking comes into play. So what it does is actually it it masks the data transmitted by the smart meters in such a way that the individual appliance signature is sort of like disappears or is masked or is hidden. But still at the distributor, the data from a group of consumers can be accurately aggregated. So, and then this accuracy depends on like over the number of consumers over which like this aggregation is taking place. So this basically data masking can help making sure that the smart meters are acceptable to consumers. It can like make them have confidence in the use of smart meters, that their data are secure. And then on the other hand, it can also like help in making sure that the normal functioning like load forecasting or data analysis by the distributors can take place. We have also worked on this topic, and we have proposed basically what can be called as lightweight approaches, that they don't need like very specific or very specific hardware computational requirements. They can be integrated within like the current hardware, current smart meters being used. And we have also analyzed the trade-off between estimation of correct aggregated value versus the obfuscation that can take place with respect to varying number of users.
Ahmed, is there any utility provider that's doing a particularly good job around data obfuscation that you can think of? Like, who's leading this practice internationally? Any shining stars?
So actually, normally here in Ontario, like really the smart meters are already like there have been a lot of smart meters. Like I think it's there's a very high like usage rate of smart meters, and as far as I know, I think most of them do have some sort of like obfuscation mechanism, and I think there are also government directives which like there are some conditions that they have to meet in order to be actually implemented in the system.
I can certainly think of, we've had at least 2 variations on smart meters in our house over the years. And so they're sitting in a box somewhere because now we have a different one. So, okay, I'm going to go to one of the questions from our participants. And they're asking us, how are we projected to reach net zero by 2050? So your research both might contribute to net zero targets. Can you talk a little bit about it? Thiago, why don't you go first?
Yeah, so as I said before, one of the applications of energy storage is to alleviate or compensate the variable nature of renewable generation. So as I said, when you talk about wind, the most energy is generated during the night. So when you talk about, for example, photovoltaic generation, it's during the day, so midday, right? So when the demand in the province is also low. So with a battery, you can, for example, save this energy when the demand is low and use it when the demand is high. So this is a good way to this contributes to the net zero program.
Great, Ahmed, do you have thoughts?
Yeah. So first thing is like to make sure, for example, like in future or like even at present, like the electric vehicles that are being used. So somehow if we can manage that, they are actually being charged with the renewable energy, because then that would in effect actually make them a net zero emitter vehicle. Then other approaches are actually to model like renewable energy generation and their sources, and then use that modeling to see how it will affect with respect to different like penetration rates in the system.
Okay, great. I'm just going to see, we don't have any more questions from the audience. I'm going to ask Thiago one more question. And if you're a participant and you have a question, this is the time to get it in, because if we're finished, then we might wrap up a little bit early. Thiago, you talked about partnering with institutions like Toronto Community Housing. If there are people who are listening today who want to consider a research collaboration or a partnership with Center for Urban Energy, what advice do you have to give them?
Yeah, so actually we are looking for partners to apply in this software and this study that we carried out for, I guess, about a year. And of course, to show them the results, to show them how could a battery, a large scale one, provide benefits, that go beyond backup power. Okay, so as I said, peak shaving, energy arbitrage, global adjustment busting, and reductions consequently in the energy bill that can go up to 50%. In fact, in our studies, we reached 53% in energy bills reduction for Class A customers of a Class A building of Toronto community housing. And from there, of course, the idea is also to implement this battery and apply our software to of course, the battery should be appropriately sized as well. Our software is able to provide a good size for the battery, and this battery should be should be also managed, because there's no point. You have to operate the battery at the appropriate time in order to perform peak shaving and global adjustment busting. So our software is also able to do that. Yeah, so of course, reach the results that we want and provide the savings for the Class A build owners.
Okay, so thank you so much. We don't seem to have extra questions coming in from. Oh, we do. We have a new one. I take that back. What does energy accessibility mean, and how are you willing to support and able to support remote communities? Either of you have thoughts? Oh. We've talked a lot about kind of centralized urban grids. Does this technology and does this research transfer to less centralized, more distributed electricity systems?
I can talk about supplying to remote communities. Basically, we need, if the grid is not able to reach this community, of course, then we would need what is called microgrid, which is basically consists of renewable generation, which can include photovoltaic and wind generation, and a battery, again, because you do not want to rely only on renewable generation. So this is the system that you should have in order to provide a continuous supply of energy with quality, and also being environmentally friendly to a remote community.
I would also just point that can be interesting, that actually electric vehicles can also serve as like a small source of electricity. So they can also help like in providing electricity when, for example, it's somehow not available or there is some situation like that.
It's amazing to think about your car as being an emergency source of power when you need it, but there you go. Okay, I want to thank both of you for your time today. We covered quite a lot of ground, I think, and made it riveting and interesting, I think, for people. I'm not sure where our attendees are visiting from, but I think you both did a really great job of helping people understand what the future of energy-related research can look like, but also how research inside the Center for Urban Energy, which is in our Urban Innovation building, can actually make a difference on the ground for a wide range of people, both in terms of cost and in consistency in terms of the electricity system, which we know now after today is particularly important just for everyday life, but also in emergencies too. So thank you so much to all of our participants. Thank you very much for coming. This session's recorded. If you sign up for our newsletter, you'll be able to come back and watch it again and share it with colleagues. Stay tuned for a new series of webinars coming from City Building TMU in the new year. I wish you all well. If you're coming in Toronto, it's a rainy, cold fall day, so stay warm. And thank you very much for coming. Take care. Bye.
Thank you.
Thank you.